Hello everyone, I'm Shrija Kombineni and today I'm going to talk about register allocation for irregular architectures. First of all, coming to introduction, in general terms, register allocation is a process of assigning variables to registers as well as managing data transfers in the registers. On the other hand, these variables can be stored or allocated in RAM, but accessing the registers is done much quicker when compared to RAM. There are two ways of doing register allocations, either local or global approach. For irregular architectures, global register allocation is still a challenging problem that has not been successfully solved so far. The graph coloring analogy of traditional approaches does not match the needs of register allocation for such architectures, which features non-orthogonal instruction sets and small register files. Therefore, a new approach to register allocation for irregular architectures has been introduced. Next, what is the importance of register allocation? Global register allocation is of vital importance for optimizing compilers. In compiler optimization, register allocation is the process of assigning local automatic variables and expression results to a limited number of processor registers. In addition to that, it speeds up the execution time of the compiled program. Next, coming to background. So, to recognize the problem, one must have thorough idea about the architectures that features non-orthogonal instruction sets and register models that are complex in nature. There are few register allocation techniques, namely graph coloring allocation, linear scan, rematerialization, coalescing, and mixed approaches. It is primary to know about these techniques. There are some concepts, namely spilling, filing, and in addition to that, it is equally important to know about symbolic registers and coloring vertices in an interference graph in register allocation. Spilling is nothing but the concept of sending a variable to memory from register, whereas filing on the other hand is shifting the variable from memory to the register. Next, coming to the approach. The approach formulates global allocation as a partitioned Boolean quadratic optimization problem, that is PBQP, that allows generic modeling of processors' peculiarities or anomalies. As PBQP is NP-complete, it is presented in a heuristic way that exhibits a nearly linear runtime complexity. The register allocator is integrated with the Infineon Caramel C compiler, which is based on the open compiler environment from Attire Software. Next, a DSP benchmark suite that was used to compare the performance of the register allocator with a graph coloring approach and with an optimal allocation. In contrast to the traditional approaches, coalescing is no longer a separate block. Copy propagation is considered as integral part of the register assignment, which is indispensable for a good register assignment. Next, another approach was introduced. So recently, register allocation based on integer linear programming, that is ILP, was introduced. This approach starts with fixing the number of free registers and then solving the minimum number of cycles to execute the instructions. Or the second approach is by fixing the maximum execution cycles for the instructions and solving the minimum number of registers that are needed. Next, coming to the conclusion, the first approach performs better than a traditional graph coloring approach for irregular architecture. It works twofold. It is an unified approach for irregular architectures, and also it is highly adaptable or highly adjustable for irregular architectures. Coalescing as an integral part of register assignment, it yields significant and better results for irregular architectures. The second approach, that is using ILP, which is integer linear programming, also worked well by accurately or precisely modeling the anomalies or peculiarities, and it provides an optimal allocation as well. Coming to the references, these are the resources that I took help to understand and tell about this topic. Thank you.